Okay. Okay. Let's begin with the chapter 2. Okay, probability distribution. Now, when we compare chapter 1 and chapter 2 class, okay, in chapter 1, what we have done is basically we deal with our data, okay, and our data as far as you are concerned, for example, if you are talking about secondary data, so it will involve more than one variable, okay. If for example, death rate, for example, for death rate data, so you will have different different types of cause of death, along with the number of death for different years. Okay, so that will be your data that you have with you. As in reverse, for what you have in the skewers measurement, the first example that we are talking about, our x. Okay, what is our x? X is our variable, and that variable reflect the interest of our study. And for the skewer project, it is reflecting what we call the length of skewers in centimeter. Okay, now what happened is that in chapter 2, okay, we are still talking about our x. Okay, we are still talking about our x. Okay, I wish I could. Okay, now we are talking about our x. Last time our x is length of skewer. Okay, in centimeter, and we call this as our variable. Okay, our variable. Now, in chapter 2, we are still talking about our x. Okay, but now our x is known as, okay, is known as random variable. Okay, it is called as random variable. It is still a variable, but we define this variable as random because of the way we choose our sample. Remember class, we have our population. Okay, so we have our population, and from our population, we cannot afford to collect all of our subject to be included in our experiment. So what we have, then we choose our sample. The way we choose our sample, okay, it will be following some sampling procedure. Okay, and this sampling procedure will basically making sure the randomness of our sample to be chosen. Okay, of our sample to be chosen. Okay, that's what we call random. Means that the way we choose our x is the same as if let's say we have 1000 skewer, the way we choose one skewer is 1 over 1000. The probability of choosing one skewer is almost the same across all 1000 skewer. Okay, now this concept of randomness, okay, will make sure that it represents your population. Okay, it represents your population. Represent the population. Now, since we know that our x can be varied, okay, this x, okay, our random variable x, if you still remember, the types of data that we can have. We can have continuous data, or we can have categorical data, or we can say also as qualitative data and quantitative data. For qualitative data, we have nominal, we have ordinal, we have interval and ratio. Okay, but for continuous data, we can basically it's just data that we need to measure. Okay, now from this particular different types of data, so that's why we are going to have different types of what we call distribution or probability distribution for our x. Okay, so we can say, if I can simplify it for you, so we have three types of probability distribution that we cover for this particular topic. Okay, so it will be binomial probability distribution. Okay, we have Poisson probability distribution, and we have the last one is continuous probability distribution. Okay, and from these two, okay, this is what we call, okay, this is what we call discrete probability distribution. Okay, as continuous remain as it is, or we call it as normal probability distribution. Now, we are going to talk about this tree a lot afterwards, and most of your test 1, quiz 1 will go back to this particular three distinction. What is discrete probability distribution, including binomial and Poisson, and your continuous probability distribution, that will be normal probability distribution. Now, if you can see the second sentence under probability distribution is quantifying uncertainty using probability. What does that mean? Okay, in order for us to talk about this x random variable, okay, knowing that this x follow certain probability distribution, okay, so there will be uncertainty for this particular x. There will be some uncertainty or certainty that involved in that particular experiment involving our x. Okay, let us look at some of the details regarding this topic. Now, based on your video task that I have assigned to you last week on Friday, okay, by now, by watching at the 7 different videos, okay, I hope by now, defining random experiment, defining outcome, event, and sample space, at least you can have the basic understanding of how we can define them. Second, define concept of probability and describe rules of probability. Okay, we will look afterwards. Okay, compare the difference between classical and empirical probability. And finally, define and give example of random variable. Okay, so you have about 7 videos. Okay, all these videos has been chosen and reflect all these what we call learning outcomes that you need to be able to understand and remember. Okay, now from these videos I have assigned you with few questions. Okay, and that few questions include: first, list the sample space for an experiment of tossing 3 coins simultaneously 3 times. What are the outcomes for an experiment of tossing 3 coins for 3 times? Okay, now let's look at your answer. Okay. Now, list the sample space for an experiment of tossing 3 coins simultaneously. Okay, I have few answers for these particular questions. And which one is the correct one? Okay, For example, this student, okay, come up with a list of what we call list of sample space for tossing 3 coins 3 times. Okay. Second sample space, most of you write this particular sample space. Okay. Is it correct or is it wrong? Some of you says number of head and tails. Definitely this is wrong. This is wrong. This is wrong. Sample space is a list of outcome that you may have if that particular experiment is being implemented. Okay, so this is not what we call as sample space. This one, yes. But among of this one and this one, which one is correct? Let us look later. Head and tail, wrong. This could be correct. This is wrong. Okay. Based on this question, the sample space is have 512 outcome. 512 is too much. Not 512. Nah? Okay, wrong. Could be correct. Okay, wrong. Could be correct. Wrong. So if you look through, there will be varieties of answer. Okay, so this one definitely wrong. This one could be correct. Okay, those who come up with sample space, potential sample space, it depends. Okay, now which one is correct actually? Now, remember the difference between list a sample space of an experiment of tossing 3 coins simultaneously. If let's say I say, okay, for 3 times, I disregard first. Okay, means I tossing 3 coins simultaneously once. What happened? You will have, okay, different outcome. Hold on. Now, let us do one experiment first. Okay, say you are tossing once. Okay, tossing your coins once. Okay, tossing 3 coins once. Okay, when you toss your coin 3 times, 3 coins once, so you will have different combination of head and tail. Since we are referring to 3 coins. Okay, coin number 1, coin number 2, coin number 3. It's either head or tail, head or tail, head or tail. Okay, so when you toss once, it could be your first outcome could be all head, for example. Head, head, head. That would be one possibility. The second possibility could be you can only have 2 head. Head, and the other one is tail. Or it could be the first is head, second and third coin, tail and tail. Or it could be what? Tail, tail, tail. Or it could be tail, head, head. Or tail, 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 head rather. Tail, head, tail. Okay, what else? Head, 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 tail, 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 head, head. tail, head, tail, head, tail. What else? We have two more. Head, tail, tail.
Head, tail, head.
Okay. Head, tail, head. And then the other one will be 1, 2, 3, 4, 5, 6, 7. The other one will be
Tail, head.
head, sudah.
Tail, tail, head.
Tail, head.
Head.
Turn. Tail, head. Okay. Okay. Tail, head. So, how many sample space do you have? Number of sample space is equal to 8. Now, when I give you this question is actually reflecting your 2.3. Okay, where we have trials in our experiment. Okay, for this particular trial, the number of trial is 1. Okay, in this example, the number of trial is 3. Okay, then when we have 3 trials with 1 trial, it will give you different what we call perspective of how we can approach this particular experiment actually, because we are repeating the same experiment, tossing 3 coins simultaneously. Instead of tossing once, you toss for the second time and you toss for the third time. And what happens is that you may have different types of what we call observation for your experiment. When you toss once, your interest is just to see what kind of combination of outcome that you may have for your once trials only. But when you increase the number of trials, it becomes different what we call perspective of approaching the problem of probability distribution. In terms of what we call sample space, okay, in terms of sample space, they are still the same. Of course, these are the outcome that can occur among the 3 trials. But let's say if you take 3 coins now, take 3 coins, okay? What happens is that when you repeat the trial, the interest is no longer which combination that will appear. The interest will be how many number of heads and how many number of tails that will occur in the first toss, in the second toss, in the third toss. So for this particular trial, okay, the interest will be different. Okay, your X is no longer depending on the what we call this particular outcome that you have. Okay, your outcome it will be different. So when you have trial, okay, of course the combination will not strictly follow this. Okay, when you toss 3 coins, you can either have, okay, let's say our X here is number of tail, number of heads, for example, number of head. Okay, number of head. Use black color. Number of head. Since we toss 3 times only, okay, so it's either no head at all, okay, 1 head, 2 head, 3 head, because we toss 3 times, right? So this will be reflecting the frequency of how this particular value occur in your experiment. So I would like to reserve this, okay, for your discussion of 2.3 when we discuss on specific probability distribution involving the discrete and continuous probability distribution. So let's say we assume, let's say, okay, I'm really sorry because when I come up with the question, I do realize that I have given you a beyond one step further from what you should understand when you do the experiment. Okay, let's say assuming we are talking about tossing three coins simultaneously once only, one trial only, not more than one trial. Okay, means that we only toss one time. Now, what are the outcome for an experiment of tossing coins? Let's say I say one time only. Okay, what are the outcomes? So if let's say you go to your textbook, okay, what is defined by outcome? An outcome is a possible result of an experiment. Result of an experiment. So which is your outcome or which are your outcome? These are all your outcome. Okay, if you are talking about what are your outcome? Outcomes are, for example, H, 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 H tail, or for example, we just take three examples, T, H, H. These are all example of outcome if you toss three coins simultaneously at once. Now, next question. What is the event in an experiment of tossing three coins for once? Okay, number 3. This is number 2. Number 3. What is the event? Look at your definition. An event is an outcome or outcome of a process whose probability is being calculated. So when you say about an event, okay, it involves probability. Okay, so when it involves probability, so what event you are talking about? If let's say the event that I'm talking about is the event of getting two hits. Okay, what event do I refer to? 2H means that I referring to event this, 2H, event this, and event this. So I have event what we call HHT, and then THH, and then HTH. Now, what is the probability? The probability of this particular event, T2H, is equal to the number of event or the number of outcome occurred, that will be 3 over the number of sample space we have is 8. Okay, so this is what we call event of getting 2H, or the probability of that particular event is this one. Okay, now number 4. Probability of an event can be greater than 1. True or false? Class, true or false?
False.
False.
Why false? Yes, false. Because why? Remember, probability can take value from 0 until 1. Not lower than 0, but and not greater than 1. It always, probability of an event is between 0 until 1. The minimum is 0, the maximum is 1. If let's say you are given a probability of an event is equal to 1.3, is that event a probability or not? So the answer is not a probability, because probability is between 0 and 1 only. Now, number 5. Probability of an event that is certainly will occur. If you look here, okay, if you look here, probability 1 and probability 0. What does that mean? If an event has a probability of 0, it means that the event is impossible to occur. Means that it will be 0. Means that it will not occur. Any probability that gives you 0 probability means that it will not occur. But if let's say, what is the probability that today is going to rain? The probability is 1. Then that means the event will certainly occur. Means that it will occur because 100% it will occur because of this value. Okay. Number 6, the value of a random variable is determined by chance of each outcome of a random experiment. Definitely. When you have your experiment, you do the experiment, that particular outcome is defined, the random variable of that particular experiment is defined by the chance of each of the outcome to occur. Okay, so that would be all the questions that you have answered, and your answer is based on 3 trials, but my discussion is based on 1 trial only, because when it involves more than 1 trials, it becomes what we call a discrete probability distribution. Okay, it's no longer basic probability distribution. Now let us continue. Do you have any questions so far, class?
Doctor.
Yes? No, no question. Okay, now let's continue. Next, what is probability then? Okay, so if you look at your textbook, probability is a numerical description of the chance of an event to occur. So if you are talking about probability of a chance, of the description of the chance of event to occur, so it reflecting your sample space, okay, which is your n of sample space, and the n of number of event occurs. That is your number of E. Okay, so we'll look at this particular details afterwards. Okay, and we know the probability value takes value from 0 to 1. Now let us look at example 2.1 on page 41. Okay, that is under 2.2 basic concepts of probability. If a family has 3 children and assume a boy is likely as a girl to at each birth, means that if you are talking about 3 children in a family, means that let's say we disregard any issues of twins or whatsoever, means that the mother will always have 1 child for each birth. Okay, now what is the sample space for the gender of children in the family? Draw using 3 diagram. So we know that assuming that there will be only 2 gender, boy or girl, not more than that. Okay, boy or girl, and we have 3 children, means that it will involve 3 births. Okay, so let's say we do it this way. Okay, okay, first child, second child, and third child. Okay, first child is either the mother will get either boy or girl. Boy or girl. Having said the first is boy, then the second can be boy or girl. Having said the first is girl, the second could be boy or could be girl. The same goes to the third child. It's either boy or girl, boy or girl, boy or girl, boy or girl. Okay, So we have what we call the first child. Okay. We have the second child and we have the third child. Now, based on this particular tree diagram, you can list out what will be your sample space for the gender of 3 children in a family. Okay, so for the first one, boy, boy, boy. So boy, boy, boy. Second is boy, boy, girl. Third, boy, girl, boy. Here. Then boy, girl, girl. Done. And then first is girl, girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And girl, girl, girl. So from this, we can list out our sample space is equal to BBB, BBG, BGB, BGG, GBB, GBG, GGB, GGG. How many S? How many sample space do we have?
8.
8. Okay, so this is your sample space of 3 children in a family. Now, define the event E if E is having one boy in the family. Now, having said that this will be your outcome. Okay, now the event E defined for you is one boy in the family. So look for all the outcomes that you have and look for one boy appeared in the family. So one boy only, this will be the first one, this will be the second one, and this will be the third one. So event E is one boy in a family of 3 children. Okay, what if I wish to highlight the event F that is 2 boys in a family of 3 child. Okay, so that will be 2 boys means that exactly it will be this one, and this one. Right. So if I list out, F is equal to BBG, BGB, and then GBB. For E just now, E is equal to one boy is BGG, GBG, and GGB. Okay, that will be defined event for the particular experiment. Now, example 2.2. So example 2.2 is for your what we call classical probability. So this is under classical probability. Now, what is classical probability? Classical probability says that to find the probability of an event is simply find the number of event E divided by the number of sample space. So that will be classical probability. Now, the question is if a family has 3 children, find the probability 2 of the children are boys. 2 of the children are boys, so we are talking about this given F. Okay, so P of F, okay, so we are talking about F, this one, 2 boys in a family. Okay, so we are talking about how many number of F occur? 3. So we have 3 over number of sample space is 8. So 3/8. Okay, as simple as that. Okay, clear class? Now, example 2.3, reflect the what we call empirical probability. Now, empirical probability based on experiment. Okay, so if this is based on experiment, then where does this come from? So if you look at example 2.3, consider the following frequency distribution of blood type obtained from a sample of 85 UNIMED students. Okay, 85 UNIMED students. Now what happened is that the experiment is that I choose 85 students. I go to the HEP. I obtained a list of names, and then I choose a sample of 85 students out of all the UNIMED students, because I need to choose the sample that represent the whole population of UNIMED students. Now, the experiment is I need to go and find each students that I have identified according to the HEP list. I go to them and I ask, what is your blood type, please? Okay, my blood type is A. Then I record one blood type A. Go to the next student, second student, my blood type is also A. Then the frequency of A increase into 2. Then I go to the third student, what is your blood type, please? Then the student say, oh, my blood type is O. I repeat the question until to the 85th student, and I ask them what is their blood type. So these are the information I got after I finished asking all the 85 students what are their blood type. So it turned out of 85, 25 students have blood type A, 15 B, 15 AB, and 0, 30. Altogether 85. Now, the way empirical probability is obtained, almost similar with what classical probability is being done. But for empirical, it is more on the trial. So this is the one that I mentioned earlier. So we have 85 students, so we ask one by one. Okay, so for this particular equation of this particular what we call question, what is the probability that a student will have blood type A? So in this case, we are going to refer to the frequency of A divided by your N. That will be 85. Number of A is 25 over 85. What about B? PB is equal to number of B, that would be 15 over 85. What about O? O is PO is equal to 30 over 85. So let us calculate then. Try and calculate 25 over 85. You will get 0.2941. 15 over 85 will give you 0.1764. 30 over 85 will give you 0.3529. Now class, my questions. What can you observe from all these probability value? Can someone answer? What can you observe from this probability value?
O has the highest probability.
Yes, probability of student with blood type O is the highest with the probability of 0.3529. means that 35% of our 85 students are having blood type O. Now, what can you observe from this uh, what we call 30 students with the probability of this one having blood type O? Other than that, what are the observations that you can observe from this particular value? What else? What can you observe? Look at the frequency. Look at the frequency of each blood type. Right? What can you observe, class? Obviously, you can see what from the frequency. Class?
B and AB has the same frequency.
That is not the what we call comments that I'm looking for. What can you observe from the probability value here with regards to the frequency?
People are more likely to have a blood O type.
Okay, I can accept that. But the things that I wish you to highlight is this. The higher the frequency, the higher the probability. Okay? The higher the frequency, the higher the probability. Definitely lah. We are talking about 25 students, 15 students, and 30 students. Definitely probability with 30 students is much higher than 15 and 25. Okay? And we know that for that particular probability, higher probability, that is the chance that it will occur. Okay, the chance for O to occur is greater than B, A, and AB. Okay, so that would be the observation that I wish you to have when you look at the difference value of probability. Now, let's look at equate exercise 2.1. Okay, two fair dice are thrown, means that you have two dice. Okay, two fair dice. Okay, each dice has 1 dot until 6 dot. Now you have two dice. Okay, you throw the two dice, okay, simultaneously. Determine sample space of the experiment. Okay, I give you 2 minutes. Can you draw on your paper what will be your tree diagram for tossing two dice simultaneously? Okay, try class for 2 minutes. Okay. Okay. Done, class? How does your tree diagram looks like? Finish, class? So you are throwing 2 dice. Of course, when you are reporting the sample size for the 2 dice, you are going to describe the possibility of having the outcome of each dice, and we combine them into our possible sample space. So in this case, okay, if you are throwing a die, 2 dice, okay, so you will have your first die and your second die. Okay, your first is either you throw the first die, you get one dot, or you get 2 dot, or you get 3 dot, or 4, or 5, or 6. Okay, 6. Right. Okay, 6. Now, if let's say you throw your dice, you get 1. Okay, how many possibility do you have for the second dice to appear? It could be having 1 dot, or 2 dot, or 3 dot, or 4 dot, 5 dot, or 6 dot. Okay, so there would be different combination of possibilities by having the second die. The same goes to if you got 2 dots, and you will get 6 more possibilities followed by the second dot. The same goes to number 3, number 4, number 5, number 6. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now let's combine their possibilities. So it could be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 5, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Right, these are all the combination. So if you wish to report the sample space of your experiment, then it will be S is equal to 1, 1, 1, 2, until the last one, that will be 6. So how many S do you have there, class?
36.
How many possibilities, huh?
36.
36, yes, correct. Okay, so second, what determine the element of event A if the outcome of both dice thrown are showing the same dots. So if you are talking about the same dots, okay, now you are talking about same dot will be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, I missed out 5, 5, and then 6, 6. So it would be event A is having the same, that will be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay. Okay. So how many A do we have? How many event A occur? 1, 2, 3, 4, 5, 6. Now number 3, the element B. Okay, number 3, the element of B, if the first thrown giving a greater number of dot than the second thrown, means that first thrown is greater than second thrown. So identify from your list of what we call outcome, sample space. 1 is greater than second. So for 1, there will be no. For 2, 1. For 2, for 3, 3, 1, 3, 2, 3, 3 cannot. So for 4, it will be 4, 1 until 4, 3. For 5, it will be 5, 1 until 5, 4. And then for 6, it will be 6, 1 until 6, 5. Okay. So for B, it will be 2, 1, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3, 5, 1, 5, 2, 5, 3, 5, 4, 6, 1, 6, 2, 6, 3, 6, 4.
Madam,
Yes.
Madam ada tulis dekat slide ke?
Yes.
Tak nampak.
Tak nampak. Oh, I forgot to share. Okay. Can you see it now?
Yes.
I forgot to continue my video. So I missed out the explanation here. So the video will start with this. Okay. So I'm really sorry, I forgot to continue to stop the post just now. Okay. So now the B, next time please let me know earlier, so that I will just rectify early. So in this case, how many number of event B? So event B will be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, well, the number of event B, it will be 15 out of 36. Now, what is the probability of event A and event B? Okay, so easily you can answer that. Okay, so we know that by using the empirical or the classical probability, we can answer this question. So for question number 4, probability of A is simply, if we are looking at the empirical, the number of event A occur is 6 over the total sample space. That will be 36. So it will be 6 over 36. Probability of B is what? 15 over 36. As simple as that. Okay. So it depends on the what are being defined as your event. Okay. For what you have now, event A is the number of same dots for each dice. And for event B is the first die is greater dot than the second die. Okay. Any questions so far, class? Any question? If no question, I will continue with the probability rule. Okay. So please look at your textbook on page 43. You have probability rules, and basically there are 4 probability rules that you need to understand, and the way you understand the whole rule will determine later if you have what we call test or quiz, conceptual explanations will be given in terms of your understanding. Okay. Now, what is the first rule that you should know? The first rule is that probability of an event E is between 0 and 1. That is understood. Means that the least probability is 0. The maximum probability of an event is always 1. Not more than 1, not less than 0. That will be the first rule. Okay. Now, the second rule. Okay, example 2.4. The second rule says is if an event E cannot occur, then the probability of event E is equal to 0. Correct lah. If that probability is given for an event is 0, means that the event will not occur. Let's look at example 2.4. Okay, example 2.4. Okay, if a single die is rolled, we are talking about a die is rolled. Okay. Okay, 1 dot, 2 dot, 3 dot. Okay, you throw a single die, so the sample space is either you get 1, you get 2, you get 3, you get 4, you get 5, or you get number 6 dot. Okay. Can someone silent your mute, please? Okay. Can someone?
Muhammad Akmal. Muhammad Akmal.
Okay. Who's on the line, please?
Muhammad Akmal.
Muhammad Fuad. Where's Muhammad Fuad? Okay. Thank you. Check share content again. Okay. Now, if let's say the example, if you roll a die, what is the probability you get 8 as your dot? Okay. You know that your maximum value of dot is 6, minimum value of dot is 1. So getting 8 dot will be definitely 0 over 6. It will give you 0 probability. Okay. What about example 2.5? The third rule refers that event E is certain to occur, then probability of event E is equal to 1. For example, example 2.5, when single die is rolled, what is the probability of getting a number less than 9? So, probability getting number or dots less than 9. Okay, so probability of getting dots less than 9, of course, is what? Okay, is either you get 1 dot or 2 dot or 3 dot or 4 dot or 5 dots or 6 dot. Okay, so it's either of these event that can occur. These are among the possibilities because as we know 6 is always less than 9. The whole number here is less than 9. So we know that is for each probability to occur is 1 over 6 plus 1 over 6 plus 1 over 6. So you will have what we call 1 over 6 plus 1 over 6 plus 1 over 6. It will be 6 over 6. That is 1. Definitely
Sorry,
it will occur. Okay, yes. Yes.
Tak nampak lagi media conteng kat slide.
Tak nampak? Okay. 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 Did you see it now?
Sudah.
Okay. Okay, thank you. Now, so if we are talking about the probability of this particular event, okay, means that we know that we have 6 dots. So what is the probability of getting less than 9? So it means if we are talking about less than 9, it could be we get 1 dot, or 2 dots, or 3 dots, or 4 dots, 5 dots, or 6 dots. Or is represented by the plus sign. So it is one of the combination from these 6 combinations. So that's why we have 6 over 6, which is 1. Definitely will get this, it will occur definitely. Okay, and the last rule is what we call the sum of all probabilities is 1. So if you are talking about probabilities of getting the dots, okay, so if let's say x is reflecting number of dots, okay, you may get 1 dot, 2 dot, 3 dot, 4 dot, 5 dot, 6 dot. Okay, so your x is the number of dots. So your probability of x random variable, where this your random variable is having the x value. So your x is number of dots. So this is your random variable. So this is your number of dots. Okay. So what is the probability of getting 1 dot? 1 over 6, like this one just now. 1 over 6. 1 over 6 also here. 1 over 6 also here. So the summation of all these probability of x is equal to for all x. Okay. For all x. So it should be capital letter. Okay. So it should be, so x is equal to x means that all x from 1 until 6 is equal to 1. You summation all these, you will get 1. So these are the 4 what we call rules that you should know. Because during the exam or quiz, we may ask you concept questions which reflect your understanding of this particular rule. Okay, so you may should start thinking of this particular rule, even though they seems to be very easy. But then if you don't understand to apply it to different situation or different experiment, it will be hard for you to what we call relate to this particular rules. Okay, now next. Now we come to the third, what we call 2.3 probability distribution. Okay, why do we call it probability distribution? Okay, and why should we know? Okay, as I mentioned earlier, your X that you are investigating could be, okay, could be following one of these. It's either binomial, it's either Poisson, or it's either continuous. Which one that the X that we are doing? Mahmud, tak apa Mahmud letak je. Kasih lah. Telefon Faizal ke tadi? Telefon Faizal ke? Oh, okay, kasih. Okay. Sorry, my husband's friend is giving some something. Okay. Okay, so before we can even know, how do we know that my X is following binomial or Poisson or normal? Okay, so these are among the concept that you should understand before we can even know which one is binomial, which one is Poisson, and which one is what we call random variable, normal probability distribution. So we have 3 only to be covered in your chapter 2. Now, let us look at the first random variable. Okay, more or less this concept I have explained earlier. We still have what we call the variable, and this variable is known as random because the variable is representing your subject from your population, and we wish to have our random variable is representing the population. Okay, So a random variable is a variable whose value are determined by chance of each outcome of a random experiment. Means that the values of a random variable is determined by chance. Okay, depending on what experiment you are talking about. If you are talking about throwing a dice which have 6 faces, then the probability is 1/6. If you are talking the experiment of tossing a coin, then the probability of tossing a coin is either head or tail. That will be 1/2 and 1/2. Or if you are talking about the experiment of, for example, of tossing a dice and a coin at the same time, then it will involve different probability. Okay, so you have 1/2 and 1/6. Okay, but that one I will not going to 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 talk in detail about that. Okay, now what is discrete random variable? From random variable we go to discrete and we go to continuous. So we have 2 types of random variable. It's either discrete or continuous. Okay, so let us look into detail. What is discrete? What is continuous? From table 2.2 in your textbook, okay, on page 45, okay, discrete random variables include number of sales, number of calls, number of questions, people in the line, mistakes per page, number of defective items. Imagine, if we are talking about number of sales, let's say we go to a handphone shop, okay? This shop selling different types of handphone, and we wish to find how many handphone that this shop can sell in one day. So the number of selling that we are referring to is exact value. How many sales do you have for today? You have 100 sales. We did not say 100.5 sales. No, it's exact value. Okay, 1 sale, 2 sales, 3 sales, 4 sales, and so on and so forth. We didn't say 1.5 sales. No, it comes with exact value. Number of calls. Let's say we go to a customer service, okay, in Telkom, for example. So we observe and we take note of how many calls the center will receive in one day. Okay, so if we are referring to a calls, definitely again it refers to exact value or number of calls occurred in that particular day. We are talking about 1 call, 2 calls, 3 calls, 4 calls. We don't say 1.5 calls. 1 call and another call is halfway. No, there is no such way. Okay, so there will be exact value of number of calls. Number of questions. If you are referring to my attendance, for example, I gave you 6 questions. So exactly the number of questions can be counted. Okay, people in the line. So if you are looking at people buying a Bazaar Ramadan at Bazaar Ramadan, if you can see a line, so you can count the number of people in the line. Okay, exact value again. Mistake per page. If you are looking for a page of paragraph, for example, a page of sentences. Okay, so what are the things that you are referring to? A typo mistake, for example. Any typo mistake is considered as mistake. So if you look at one page of what we call full of sentences, you can count the number of mistake or typo mistake that you can have. So exactly, again, it will be exact value. The same with defective item. Okay, exact value again. But now look at the continuous random variable. For continuous random variable, so if you can see, it needs to be measured. Okay, for here, counted. You can count that. So for example, length of skewers, you need to measure. Depth of a swimming pool, for example, you need to measure. Okay, volume, you need to measure. Okay, time, weight, daily rainfall. All these examples need to be measured according to their respective measurement. Okay, so these are the difference between discrete and continuous random variable. Okay, now let's say I give you a question. I give you equations of the number of the number of the number of books. The number of books, is it continuous or discrete? Class,
Discrete.
number of books, discrete, yes. The the length of the length of table, for example, the length ada kat sini lah. What else? Okay, tak adik lah. It's okay lah. You can see clearly the difference between discrete random variable and what we call continuous random variable. Okay. Do you have any question here, class? Do you have any question here?
No, madam.
Okay, no. If no, then we go to discrete probability distribution. We know under discrete probability distribution, we may have binomial or we can have Poisson. For binomial probability distribution or Poisson probability distribution. Now we know how it becomes discrete and we know how it becomes continuous now. But now from here we know it can be either one of these. How should we know? How should we know it follows binomial or it follows Poisson? Okay, let us look at the details. A discrete probability distribution consists of possible values a discrete random variable can assume and their corresponding probability. Okay, so means that for probability discrete probability distribution, okay, it will follow certain what we call characteristic and it will follow certain probability distribution for that particular random variable, discrete random variable. So now, let's assume that x is your, okay, x is a discrete random variable. Discrete random variable. Okay, and we know that probability of x is equal to x, okay, is read as probability of x exactly equal to x. So means that this x is a number. Okay, this is a number. Equal to what? 1, 0, 3, 5, whatever number that you can have, depending on the experiment that you are referring to. Now, first, we know that our x is discrete random variable. Second, probability of this random variable is equal to one value is defined as probability of x exactly equal to x. Now, it says that a discrete probability distribution must satisfy the following condition. So there will be two conditions that it should satisfy to be a discrete probability distribution. So these are the conditions that should be fulfilled. Okay, the first condition is that, okay, probability of x is equal to certain value is from 0 until 1. This is the probability rule that we have just discussed. Means that for any discrete random variable, the probability is between 0 and 1. The second characteristic is that, or the second condition is that the summation of all the probability, okay, for x, okay, the summation of all x, taking any value of x from, for example, x is in the sample space, the summation is 1. Okay, so this will be your what we call characteristic or condition that should fulfill what we call the discrete probability distribution. Okay, now since we have half an hour more, so I would like to go to the basic of discrete probability before we can go into how we can define it will be binomial or it will be Poisson. Okay, so as we know that probability distribution can be in terms of table, in terms of graph, or in terms of mathematical formula. Now, if you look at page 45, okay, if you look at page 45, okay, in the description for this particular example 2.1, okay, we are talking about having 3 children in a family. Okay, let's say in this particular what we call experiment, this x, the random variable x is the number of boys in a family of 3 children. Now, this is very important class. This big capital letter X here is what we call our random variable. And this random variable is defined as the number of boys in a family. Okay, so when we talk about the number of boys, it could be no boys at all, or in maximum, they could be 3 boys in a family. So if we put into what we call a table of distribution with the probability, so this is what we have. Okay, the outcome of your x here is the number of boys. 0 boy, 1 boy, 2 boys, 3 boys. And what are the possible outcomes? Reflecting 0 boy means that all the children are girls. Or 1 boy, where the first and second is girl and the third is boy. Second is boy, the first is boy. Okay, so you will have how many event here? 3. How many possibility? 8. So that's why we have for 1 boy in a family, the probability is 3/8. For 0 boy in a family, since we have 1 event for all girl, the probability is 1/8. For 2 boys in the family, means that first, second boy, first, third boy, second and third boy. So again, 3/8. And if we have all boys, okay, all boys means that the number of boys is 3. So the probability is 1/8. Now check. Okay, check. Is the probability for each of the event is between 0 and 1? Yes, 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 yes. For condition number 1. For condition number 2, okay, the probability, if we sum all the probability, P of x is equal to x, where x is equal to 8. In this case, it's equal to 3. Yeah? Okay, never mind. Just don't want to confuse you. Okay, so just put this way. Okay, the summation of all the summation of all the x from 0 until 3 is equal to 1. How? 1 over 8 plus 3 over 8 plus 3 over 8 plus 1 over 8 is 8 over 8 is equal to 1. So fulfill. So means that those conditions are fulfilled now. Okay. If you wish to draw this into your what we call probability distribution, okay. So from here you go to what we call probability distribution. How it becomes a probability distribution is by using the table that we have. Okay, your x will be number of boys from 0 boy 1 2 3, and this is your frequency. Okay, this is your frequency. Sorry, this is your probability. Okay, so this is your probability. Okay, for having one children, okay, so you will have 1 over 8. 1 over 8, for example. For having one boy, so you will have 3 over 8. Okay, two boys also 3 over 8. Okay, for 3 boys, it's only 1 over 8. So you can see that the probability distribution for this particular experiment looks like this if you were to draw using histogram. Okay, so this is what we call probability distribution. Okay, now next we are going to look into how it becomes binomial and how it becomes Poisson. How to differentiate which is which. Okay, so for this one, I think I'll just cover in the next class after the semester break. Okay, any questions so far? Any question regarding the materials that we have just discussed? Right? No questions. Okay, if you don't have any question, I'll just stop sharing. Okay, stop recording.